get the values. Now in the same signal we are going to do a small change in that, so that we can get a better conversion of a signal into a frequency domain. So that is your discrete Fourier transform. So discrete Fourier transform provides us a mechanism for numerically computing the discrete time Fourier transform. So here the values are given, you will be getting data, right? So it is a numerically computed discrete time Fourier transform. So in DFT you will be getting values for each instance. All right, so you are going to get mathematically computed numerical values. It also alerts us the potential problem of aliasing in the time domain. So using a discrete time Fourier transform, the aliasing can be completely eliminated. What is that aliasing? Overlap of signals. So overlapping of the signal happens most of the time due to the sampling. So in the sampling, if you remember, in a lab we choose Fs as 2 times of maximum frequency, greater than 2 times of your maximum frequency. Why is that? Because to avoid aliasing. What is that Fs greater than 2 times of Fs? That is called Nyquist criteria. So using a Nyquist criteria, we are choosing the sampling frequency twice greater than the maximum frequency. So that is used to avoid the aliasing. But in the discrete Fourier transform, there is no case of aliasing, provided there is a condition. We'll come to that. Then mathematics dictates that the sampling of the discrete time Fourier transform result in a periodic sequence. What is that meaning? So if I have an input x of n, and if I'm taking discrete Fourier transform DFT, so I'll be getting, assume I'm getting x of k. Now if I take IDFT, inverse discrete Fourier transform, to reconstruct my original signal back, I'll be getting xp of n. What is that? What is the difference between x of n and xp of n? Is xp of n is a periodic version of your x of n. So the reconstructed signal is going to be periodic. All right, but here this x of k and xp of n, we are not going to see outside the n value, the given sampling point. So if you are seeing outside the sampling point, it is going to be periodic, it is going to be repeated. What is the periodic signal? It will repeat. So that signal xp of n will be repeating again and again. It's a periodic signal. But the x of n need not to be a periodic signal, it can be a aperiodic signal. So when I do a DFT, so I will be taking a sample, I will be taking n point or L point. That point, that values, that sequences are taken for discrete Fourier transform. So I will get x of k. Then if I reconstruct that, that will end up with the xp of n. Even though the main point is, even though it is xp of n, we will be concerned about only the x of n. We are not going to see outside the x of n. If you want to expand, you can expand. All right, if you want to expand your x of n, you can expand, and that is going to be periodic. All right. Practically, a new transform called discrete Fourier transform is defined, which is the primary period of DFS, discrete Fourier series. The DFT is an ultimate numerically computable Fourier transform. Please make a note of it. DFT is the ultimate numerically computable Fourier transform. In the discrete time Fourier transform, if you remember, I mentioned about one condition. It should be absolutely summable. All right. But in the case of DFT, it is ultimate numerically computable Fourier transform for arbitrary finite duration sequences. Please underline the word finite duration sequences, because you are not going to take an infinite series. Your input x of n, remember that point, your x of n, I said it's not necessarily a periodic signal. Even though it is a aperiodic signal, we are not going to take the whole signal. We are going to take a finite sequence, right? 8 point or 16 point or 1024 point or 2048 point, like that. So we are going to take a finite sequence. You get the point? So this is your DFT is going to be as I mentioned in the first slide, it is going to give me a number, a value. It is a numerically computable Fourier transform. Right. Now what is that DFT? So in DFT, in DTFT, x of omega, what is x of omega? Summation n tends to minus infinity to infinity x of n e power minus j omega n. Am I right? Now please listen, you can take it a little later. So now this x of omega, what is that x of omega? It is the spectrum, right? Yeah, the spectrum in terms of omega. Now this spectrum, say for an example, you have a signal like this. This is your x of omega. So this x of omega, will it be a periodic or aperiodic? X of omega. What is your x-axis? Omega. What will be the range of omega? 0 to 2 pi. Right? It is omega. It's a frequency term. It should be 0 to 2 pi. So it is x of omega. It is periodic with a period of 2 pi. Right? So in an interval of 2 pi, it is periodic. So again, 1 to 2 pi, then again 0, then again 2 pi. It's like a circle. Am I right? So this is omega. If start from 0, all right, this is pi by 2, pi, 3 pi by 2, 2 pi. All right, then again it will start. So it is a periodic version. Now what we are going to do here, this signal, please listen very carefully. This is your x of omega. Till this, is that clear? Now this is your discrete time Fourier transform. Now to get discrete Fourier transform, we are going to sample this x of omega. That's all. So DFT, it is nothing but it's a sampled version of DTFT. All right. So what I'm going to do, I'm not going to take it as a continuous signal. I'm going to sample it. All right. So what will be the interval? It's a uniform sample, right? What will be the interval? What is the maximum distance? 2 pi by what is that n? Number of samples. So number of samples. So this interval. So what I'm going to do, I'm going to replace this as x of omega k. All right. So what is omega k? This omega k, I'm going to replace it with 2 pi by n. All right. Now your DFT. So if you put that, x of 2 pi by n. Now for each sample, I need to give an index. 0, 1, 2, 3, 4, isn't it? So that is k. K is the index of the sampling point. So that will be summation here. It's not going to be minus infinity to infinity. Here it's going to be 0 to n minus 1, because I'm going to take only n points. The total number of points are going to be n. So when I started from 0, it will be n minus 1 x of n e power minus j. In place of omega k, we put 2 pi by n into kn. So this comes in the place of omega k. So again I repeat, DFT, it is the sampled version of discrete time Fourier transform. So we are sampling the x of omega in the interval of 2 pi by n, of course with the index k. So k, what is the running length of k? So here the k will be 0 to n minus 1. So that is your DFT. So DFT is n 0 to n minus 1 x of n e power minus j 2 pi by n into kn, where n is taken care by the summation, k you have to write. So k will be 0 to n minus 1. So this k also part of your DFT formula. Alright. So now what about the inverse? As I said in the previous class, every transforming technique will have a inverse transform. So the inverse discrete Fourier transform, where we get x of n back, and based on our discussion that x of n is going to be discrete, it's a periodic version. So x of n is 1 by n summation k 0 to n minus 1 x of k e j 2 pi kn by n. So I can simplify this because this is going to be same for all the case. Alright, so I can simplify this as x of k and similarly the inverse DFT, I'll get my x of n back by taking 1 by n summation. Please remember that the small x stands for the input and the capital X stands for the DFT, right? Transformed version. Now the basic difference, one very important point, the basic difference between your forward DFT and the reverse DFT is the polarity. I mean, of course, this factor, other than 1 by n factor, it is the conjugate of the forward direction. So this point will be very useful in your next algorithm, that is fast Fourier transform. Now just keep that in mind. The difference between your DFT and IDFT is that minus factor, right? Now of course here n will be 0 to n minus 1 because k is taken care by the summation. Alright, now we are going to introduce another factor here. So this is your DFT and this is your IDFT. So in that, n minus 1 x of n, in place of that exponential term, I'm going to introduce another factor called weight matrix. Okay, please make a note of it. The weight matrix is given by Wn, where Wn is given by e power minus j 2 pi by n. So here I need to put kn separately. Actually this Wn is the weight matrix. Okay, so the Wn is the weight matrix, and in that weight matrix, to incorporate this kn, because your DFT formula, you see there is a kn value. So to include that, your weight matrix, the final weight matrix will be W of n kn. So what is W of n kn? Right. So here there is one small twist is there. The minus will be taken in the weight. Okay, W of n means it includes minus. So now if you are writing your inverse 1 by n k n minus 1 x of k W of n minus kn, you should not get confused with this minus, because actual formula there is no minus for IDFT. Since you are introducing the same weight which you used in the DFT, you have to put minus there. Is that clear? Alright, so this is called weight matrix. Alright, now this is the basic idea of discrete Fourier transform, and this is how we mathematically calculate discrete time Fourier transform. Alright, now let me give you one example. X of n one one two two 1 1 1 1. So what is the n value here? N is 8. Please listen. Why, this is the length of the input sequence. The length of the input sequence is given as L. Alright. N is the length of your DFT. Right. Now if L is greater than N, what will happen? Right. Do you understand? So here in the example, what is L? L is 8. Alright. Now if I are interested in finding a 4-point DFT, now L is greater than N. So finally when you are getting X of k, there will be only 4 values. You understand? Now if you are reconstructing it, right, your X of n or xp of n, just to differentiate, xp of n will have only 4 values. So you will be losing the remaining 4 inputs. So that is called aliasing. So the next period will get overlapped with the first period. So the first period is incomplete. You are not getting 8 values, you are getting 4 values. So now in case of n greater than L, what will happen? When you are reconstructing it, say if n is 10 and L is 8, alright, when you are your X of n will have 8 values, and when you are taking a DFT, again you will get 8 values. Alright, when you are reconstructing it, when you are doing a DFT, you will get 10 values, but the last 2 values will be 0, right? And when you are reconstructing, instead of 8 you will get 10. There is no harm, right? You are not losing any information, right? But this one is going to harm your input, right? You are going to miss some data. There is a data loss. So this L greater than N is not suitable condition. It can be N greater than L or N equals to L. I hope you understand what is N and L. N is the DFT, length of your DFT. L is your length of input. Now suppose if there is a case where L is greater than N, what you have to do? You have to use zero padding. So there only you will be using zero padding. Say for an example, in this case L is 8, right? So your N is 4. Then you have to use 8-point DFT, not the 4-point DFT. Okay, so that is how we manage. Now in the given example X of n, it is 8, and your DFT also you are expected to do an 8-point DFT. So what is the formula? X of k is 0 to, what is the running length of n and k? 7. X of n e power minus j 2 pi by 8. It is not n minus 1, it is n into kn, where k will be 0 to 7. Now X of 0 will be X of n e power minus j 2 pi by 8, 0 into n, because k is 0. So this exponential term is going to be 0. Whatever value of n, no matter of the n, it is going to be 0 always. So e power 0 is going to be 1. So x of 0 is x of n. So it is 1 plus 1 plus 2 plus 2 plus, it is 10. Now can you do x of 1? Please try x of 1. 0 to 7, x of n e power minus j. Please listen here, I can make some simplification in the beginning itself, because it's 2 by 8, I can make it as pi by 4 in the beginning itself. So pi by 4, k is 1 into n. Expand this, x of 0 e power minus j pi by 4 1 0 plus x of 1 e power minus j pi by 4 1 into 1. Similarly it go up to 7, x of 7 e power minus j pi by 4 1 7. All right, so 1 plus, because this is going to be 1, you have 0 e power 0, so e power 0 is 1 plus 1 into e power minus j pi by 4. It is cos pi by 4 minus j sin pi by 4. It will be minus 0.707. Please take it down. And x of 2 is 2 into e power minus j pi by 2. So e power minus j pi by 2 is minus j. Alright, so it is x of 3. X of 3 is again 2 into e power j 3 pi by 4. The answer is, when you simplify it, minus 0.707 minus j 1.707. X of 2. So like that you have to find up to x of 7. So x of 2, I'll just write the formula. Two n. So when you are doing 2n, right, and of course the first term n is going to be 0, so 1 plus 1 into e power pi by 2 minus j plus 2 into e power minus j pi plus 2 into e power 3 pi by 2 So pi by 2 minus j, and this is minus 1. 2 pi is 1. This is plus j, and this is again minus j. This is minus 1. This is minus j, right? So the answer is minus 1 plus j. So now if you do like this, x of 3, again you will be getting and x of 4 will be 0. Now for getting the remaining values, okay, so you are supposed to get x of 0 to x of 7. Now what you have done, you have found out up to x of n by 2, that is x of 4. Now for x of 5, x of 6 and x of 7, you have to use a property called symmetry property. All right, right, the symmetrical property says that x of k is given by x star of n minus k, meaning x of 5, that's what we need, is x conjugate of 8 minus 5, that is x conjugate of 3. So what is x of 3? 0.707 plus j 0.293. When you take a conjugate, what is the complex conjugate? Only the complex term, you will take the opposite. Alright, so this is going to be our x of 5. So this is a very, very important property. It's a symmetrical property of discrete Fourier transform. Now x of 6 will be x conjugate of 8 minus 6, that is x conjugate of 2. So x of 2 is minus 1 plus j. So conjugate will be minus 1 minus j. And x of 7, x conjugate of 8 minus 7, that is x conjugate of 1. So it is am I right? What was the x of 1? What was x of 1? Was it minus or plus? This is plus. Alright. Now, so you have to, the last step is you have to write all the x of k's as a sequence. Write all the x of k as a sequence. This 10, alright. Now find the absolute value of x of k. Please find the absolute value of x of k. Absolute value, how will you find out? So 10. The other values? And the very last step is plotting the magnitude function. This is how you have to find the spectrum of any given input sequence. So now what we have done, we have found out the discrete Fourier transform of a given sequence. What was the given sequence? 1 1 2 2 1 1 1 1. You know, that's an input, that's an uh, part of your input signal. So we have taken 8 point of the input sequence and we have done 8 point DFT. Then we have taken the absolute of that, we have plot that function with respect to k. So this is your frequency spectrum of the given input sequence. All right, any questions? No need, no need, no need. We have already used one of the property, that is the symmetric property. So symmetric property is very important because whenever you are using when you are finding a DFT, actually the symmetric property is applicable either way, right? Say if you are finding out x of 7, x of 6 and x of 5 first, then you can find out x of 1, x of 2, x of 3 from that, right? But actually we normally do x of 0, x of 1, x of 2. So the remaining, the second part, we can find out using the symmetrical property, right? Now the very important, so we I have listed some very important properties of DFT. The first one is linearity. So the DFT, what is the linearity? In previous classes we have discussed about linearity of a system. How will you define a system is linear? It has to obey the superposition theorem. All right, so the DFT, you know, if you consider DFT as a system, it is a linear system, meaning if you take DFT of the summed inputs, please listen, I am taking x of x1 plus x2, then I am taking DFT of the summed version is going to be equal when I do DFT individually to x1 and x2 and sum it. You understand? That is, DFT of x1 plus x2 is going to be equal to DFT of x1 plus DFT of x2. So this is true in case of DFT. That is why DFT is a linear system. Then circular folding. Why it is circular folding? Why it is not shifting? Because the signal is periodic. So since the signal is periodic, we are talking about the folding, circular folding. So what is this symbol? It is the mod operation. Okay, x of minus n mod n, x of minus n mod n. Okay, that is the notation we normally use for circular shift, circular rotation. Right, now the x of n, if you are rotating by k, so if I have x of n and which is going to give me x of k when I do discrete Fourier transform. Now what I'm going to do, I'm going to shift this x of n, or I'm going to circularly rotate this x of n by m unit, right? In circular convolution we have studied about it. So x of n minus m mod n, meaning you can say there is a circle Please listen very carefully. It's a circle and you are spreading the input. So there are how many points? 4 points. All right. So you can rotate, one complete rotation you can rotate 4 times. That's all. Maximum you can rotate 4 times. So that is m. So your m should be between 0 to n minus 1 time. You understand? See, 0 to n minus 1 time. So m is the number of times. It can be 0. If it is 0, it is going to be x of n. It can be x of n minus 1. So I am rotating 1 time. X of n minus 2. I am rotating 2 times. It can be x of n minus 3. 3 times. Only that is possible for one cycle because I have only 4 points. Alright. So in that case, x of n minus m mod n, if I take the DFT of this, it is going to be e power minus j 2 pi by n k m x of k. Please take it down. This is the circular shift property. So what is the circular shift property? So here understand that this is not n, this is m. The shifting unit, how many rotations you are shifting, into what is this x of k? X of k is the original DFT of my unshifted, unrotated input. So for a shifted version, please listen, your x of n is 1, then I am shifting it. Alright, now I want to take the DFT of the shifted one, then I don't have to do the DFT as a whole again. I don't have to do it. I just need to multiply my old DFT with this factor. That will give me the required output. Are you getting the point? So that is the circular folding or circular shift. Then conjugation, complex conjugation. Say DFT of x star of n. It's very simple. Again, for every property, this is the bottom line. Your x of n is going to give me x of k, right? X of n, the original input. Now if you take the conjugate of x of n, right, your DFT will also be conjugate of x of k. Alright, so x of n is giving x of k and I am taking conjugate of input x of x star of n, so my output will also be conjugate x star of k. Then symmetrical property, that's very, very important, that we have already discussed about it. X of k is going to be x star of n minus k. In all these properties we will be using this very often because this will be helpful for computation, calculation. So x of k is going to be x star of n minus k. So for any say for an example, if it is a 16-point DFT, you don't have to do all the 16 points. You just have to do only 8 points. In that also, your x of 0, please listen, it's very, very important. It's a very important question, DFT. I'm trying to simplify it. So x of 0, consider you are doing an 8-point DFT. X of 0, it is nothing, just addition of all the given sequences, just sum of all the sequences. Why? Because e power 0 is going to be 1, so it is x of n. Just add all the x of n. X of 2 you have to find out, x of 1 of course, x of 1, x of 2, x of 3 you have to find out. X of n by 2 is, please take it down, it is the difference of even indexed value and the odd indexed values. Meaning, let me explain it with that same example. This is your input. So here, please listen. This is x of 0. Am I right? This is x of 1. So this is called even indexed value. This is odd indexed value. So add all the even indexed value and add all the odd indexed value. Take the difference, that's going to be our x of n by 2. Okay, what was the answer in that example? It was 0 because 1 plus 2 plus 1 plus 1, it is 5. minus 1 plus 2 plus 1 plus 1, 5, 0. Are you getting that? Let me give you one example. Find x of 0 and x of 4. Please tell me that. So how will you do x of 0? Just add all the given inputs. So it is 1, 7. What about x of 4? Add all the even indexed values, then add all the odd indexed value, take the difference. Even minus odd, minus 7. So for a 8-point DFT, we have found out x of 0, x of 4. Just by mathematical addition and subtraction, you can find out x of 0 and x of 4. X of 5, 6, 7, you can use symmetrical property. So actually you are going to do the mathematical computation for only 3 points, 1, 2 and 3. You understand? But if you do any small mistake in this 1, 2 and 3, you know, it will reflect in your the other part also. So you'll be losing 2 points, right? You'll be making mistake in 2 points. Is that clear? So this is how you can simply do DFT. And the other property, the circular shift, that's what we have seen. Please take it down. In frequency domain, the x of 4, is there any different answer? Huh? It's correct? Yeah. So in the circular shift, there are 2 variants in it. Circular shift in the time domain, you are shifting the input, right? If there is a shift in the output, that is in the frequency, then it will be replicated in the input. So what is this? Wn minus Ln. It is e power j 2 pi by n Ln. Minus won't be there. You understand? So this is the actual expansion of this. If there is a minus in the weight, please remember, if there is a minus in the weight, you have to leave that minus when you expand that. You know, only in DFT. Then circular convolution. Circular convolution we did in 2 different methods in the normal class. With the DFT, you can make it very simple. Circular convolution of any 2 sequences in using DFT is just the multiplication. Alright. So if you have two sequences, x1 of n, x2 of n, please listen, this is very important, we will be doing this in the lab. So x1 of n and x2 of n, if you want to do circular convolution, what you need to do, you just take DFT of that, you'll be getting x1 of k. Take the DFT of this, you'll be getting x2 of k. Multiply this two, right? So let me take it as x3 of k, which is x1 of k into a normal multiplication. Then take the IDFT of this. That will give you x3 of n. This is the required circular convolution. Do you understand the sequence? I have 2 inputs, x1 of n and x2 of n. Take the DFT separately, multiply that, you'll be getting one term. Then take the inverse of that. That will be your circular convolution in time domain. Alright. Now in case of a linear convolution, can we do linear convolution out of this DFT? Yeah, I'll just skip this. This we already done. For linear convolution, what you have to do? So what is the difference between circular convolution and linear convolution? Circular convolution, number of output will be same as your number of input. So no problem, you are getting a 4 input sequence, you will be getting 4 input 4 input sequence in the output. That's your circular convolution. What about linear convolution? So if you want to do linear convolution, you have to do so x1 of n, it's a 4 input sequence. Please listen very carefully. x2 of n, you have a 3 input sequence. All right. Now what is the expected y of n? 7, isn't it? 4, I'm sorry, 6. 4 plus 3 minus 1, 6. So here we have only 4 inputs. So you need to fill 2 zeros here. All right. How will you know about it? So total length is n plus m minus 1. Already you have n. Okay. So n will get cancelled. So in the first sequence you have to fill m minus 1 zeros. What is m? Length of my second sequence. The second sequence is 3. 3 minus 1, 2. So I have to fill 2 zeros. Now coming to here, it is n plus m minus 1 minus m. What is this m? What is already available, that you have to minus. So m will get cancelled. N minus 1 zeros. So you have to put 3 zeros. So now what I am doing is I am making both the input sequences of same length. What is that length? 6 and 6. Now I do 6 point DFT of 2, I mean the same procedure. 2 DFT, 2 6 point DFT, multiply it, take the inverse. The result is going to be linear or circular? The result is going to be linear convolution. Alright. If you are going to leave it as it is and you are finding out that, the result will be circular convolution. If you do zero padding and do the procedure, the result is going to be linear convolution. So using DFT, you can do both circular as well as linear convolution. Is that clear? The same DFT can be implemented using a matrix method that we will continue in the next class.